What if I told you that somewhere in our universe, an explosion happened that was so massive, so incomprehensibly powerful, that it carved out a cavity in space large enough to fit 15 Milky Way galaxies side by side? What if I told you that this explosion released more energy than our sun will produce over its entire 10 billion year lifetime, multiplied by a trillion times? And what if I told you that this explosion happened not in some distant corner of the cosmos during the universe's violent youth, but relatively recently in what astronomers call our cosmic neighborhood? This isn't science fiction. This isn't speculation. This is the story of the most powerful explosion ever detected since the Big Bang itself, an event so extraordinary that it has forced us to rewrite our understanding of what's possible in the universe. This is the story of the Ophiuchus supercluster explosion, and today we're going to unravel one of the most mind-bending discoveries in modern astronomy. Picture this. You're standing in your backyard on a clear night looking up at the constellation Ophiuchus, the serpent bearer. It's a fairly unremarkable patch of sky to the naked eye, just another collection of distant stars forming ancient patterns that our ancestors traced across the darkness. But hidden within that seemingly peaceful region of space lies evidence of a catastrophe so immense that it challenges everything we thought we knew about the limits of cosmic violence. The explosion we're talking about didn't happen yesterday or even a million years ago. It occurred roughly 390 million years ago, when life on Earth was just beginning to crawl out of the oceans. Dinosaurs wouldn't exist for another 150 million years. Humans wouldn't appear for nearly 390 million more. And yet, the aftermath of this explosion is still visible today, still shaping the cosmic landscape around it, still telling its incredible story to anyone with the right instruments to listen. But here's what makes this discovery so remarkable. We almost missed it entirely. For decades, astronomers had been studying the Ophiuchus galaxy cluster, one of the nearest major galaxy clusters to our own Milky Way. They knew it was there. They'd mapped its galaxies, measured its mass, cataloged its properties. It seemed like a fairly typical example of what happens when hundreds of galaxies bind together under their mutual gravitational attraction. Nothing particularly special, nothing that would make headlines or revolutionize our understanding of the universe. Then, in 2016, a team of astronomers led by Simona Giacintucci at the Naval Research Laboratory decided to take another look. They weren't hunting for the discovery of the century. They were simply trying to understand some unusual features they'd noticed in radio telescope observations of the cluster. There seemed to be something odd about the distribution of hot gas surrounding the central galaxy, something that didn't quite fit the standard models of how galaxy clusters should behave. What they found defied belief. Hidden in the X-ray images taken by NASA's Chandra X-ray Observatory was a giant cavity, a bubble of empty space carved out of the hot gas that permeates the cluster. At first, they thought it might be an instrumental error or perhaps some kind of data processing artifact. Cavities like this weren't entirely unknown in galaxy clusters, but they were usually much smaller, created by jets of material shooting out from supermassive black holes at the centers of galaxies. But as they analyzed the data more carefully, as they combined observations from multiple telescopes and studied the structure from every angle they could imagine, an incredible truth began to emerge. This wasn't just any cavity. This was a wound in space itself, a scar left by an explosion so powerful that it had literally blown a hole in the universe's largest gravitationally bound structures. To understand just how extraordinary this discovery is, we need to zoom out and think about the cosmic context. Galaxy clusters are among the most massive objects in the universe. The Ophiuchus cluster contains hundreds of individual galaxies, each containing billions of stars, all held together by dark matter scaffolding that outweighs all the visible matter by a factor of 5 to 1. The total mass of this cluster is roughly a quadrillion times the mass of our Sun. That's a number so large it loses all meaning in human terms, but imagine trying to move something that massive, trying to carve a cavity in it, trying to reshape it through sheer explosive force. The cavity that Giacintucci and her team discovered spans about 1.5 million light-years across. To put that in perspective, the distance from Earth to our nearest major galactic neighbor, Andromeda, is about 2.5 million light-years. This explosion carved out a hole in space that's more than half that distance in diameter. If you could somehow shrink the Milky Way down to the size of a quarter, this cavity would be the size of a football field. But size is just one measure of this explosion's incredible power. To create a cavity this large in such a dense environment requires energy on a scale that pushes the boundaries of what physics tells us should be possible. When astronomers calculated the minimum energy needed to blow such a hole in the Ophiuchus cluster, they arrived at a number that made them double-check their math, roughly 5 times 10 to the 54th power joules. That's 5 followed by 54 zeros, an amount of energy that makes nuclear weapons look like firecrackers and supernovas look like birthday candles. To give you some sense of this scale, consider that our Sun, which has been burning steadily for 4.6 billion years and will continue burning for another 5 billion years, will produce about 10 to the 44th power joules over its entire lifetime. The Ophiuchus explosion released roughly 5 billion times more energy than that. If you could somehow harness all the energy our Sun will ever produce and release it in a single instant, you'd still need to repeat that process 5 billion times to match what happened in Ophiuchus. But here's where the story gets even more incredible. This wasn't just a lot of energy released quickly. This was a sustained explosion, an event that continued pumping energy into the surrounding environment for millions of years. Think of it not as a brief flash, but as a cosmic blowtorch that stayed lit for longer than complex life has existed on Earth, steadily carving out this enormous cavity and reshaping the distribution of matter across millions of light years. What could possibly cause such an explosion? This is where we need to journey into the heart of one of the universe's most extreme environments, the immediate vicinity of a supermassive black hole. At the center of nearly every large galaxy sits a black hole millions or billions of times more massive than our Sun. These aren't the stellar mass black holes created when individual stars collapse, but true monsters, cosmic vacuum cleaners that can devour entire solar systems without noticing. But black holes, despite their fearsome reputation, don't just consume everything around them indiscriminately. When matter falls toward a black hole, it doesn't simply disappear. First, it forms what astronomers call an accretion disk, a swirling spiral of superheated gas and dust that glows brilliantly as it spirals inward. The friction in this disk heats the material to millions of degrees, creating one of the brightest phenomena in the universe, an active galactic nucleus, or quasar. Now, here's the crucial part. Not all of this material actually falls into the black hole. Some of it gets caught up in the black hole's magnetic field and accelerated to nearly the speed of light, shooting out from the poles of the black hole in narrow focused beams called jets. These jets can extend for millions of light years, carrying enormous amounts of energy and momentum far from the black hole that created them. Under normal circumstances, these jets carve out relatively modest cavities in the hot gas surrounding their host galaxy. We see this happening in galaxy clusters throughout the universe, and it's one of the ways that supermassive black holes regulate star formation in their host galaxies, preventing them from growing too large by heating up and dispersing the gas that would otherwise condense into new stars. But what happened in Ophiuchus was anything but normal. The central galaxy of this cluster, known somewhat unimaginatively as the Brightest Cluster Galaxy, or BCG, harbors a supermassive black hole that appears to have gone through a period of activity so intense that it created jets powerful enough to blow this enormous cavity in the cluster's hot gas. We're not just talking about a brief burst of activity here, but a sustained period of extreme jet production that lasted for tens of millions of years. Think of it like this. Imagine you're inflating a balloon inside a swimming pool filled with thick honey. Under normal circumstances, you might be able to create a small bubble, but the resistance of the honey would limit how large it could grow. But if you had access to an industrial air compressor and could keep pumping air for hours, you might eventually create a bubble large enough to displace significant amounts of honey. That's essentially what happened in Ophiuchus, except instead of honey, we're talking about hot ionized gas, And instead of an air compressor, we're talking about one of the most powerful forces in the universe, a supermassive black hole jet system operating at maximum capacity for geological timescales. But this raises a fascinating question that gets to the heart of one of astronomy's biggest mysteries. What triggered such extreme activity in the first place? Supermassive black holes don't just randomly decide to become hyperactive. Something had to happen to feed enormous amounts of material to the central black hole, something that kicked it into the highest possible gear and kept it there for millions of years. One possibility is a galactic collision or merger. When galaxies collide, their interactions can funnel vast amounts of gas and dust toward the center of the resulting merged galaxy, providing fuel for the central black hole to consume. We know that galaxy mergers were much more common in the early universe, when galaxies were smaller and closer together, and we can see evidence of ongoing mergers in many galaxy clusters today. But there's a problem with this explanation. Galaxy mergers, even major ones, typically don't provide enough sustained fuel to power jets this energetic for this long. Most merger-triggered activity in galactic nuclei lasts for perhaps millions of years, not the tens of millions that would be required to carve out the Ophiuchus cavity. We need something more extreme, more sustained, more capable of feeding a supermassive black hole on the scale required. Another possibility is what astronomers call a cold flow, a stream of primordial gas from the cosmic web that somehow avoided being heated up during the universe's early history and remained cold enough to condense directly into the galaxy cluster. These cold flows can provide a steady supply of fuel for supermassive black holes, potentially sustaining high levels of activity for much longer periods than galaxy mergers. But even this explanation struggles to account for the sheer scale of what happened in Ophiuchus. We're talking about an explosion that represents one of the most energetic events ever observed in the universe, something that approaches the theoretical limits of what should be possible given our understanding of black hole physics and jet formation. This brings us to one of the most intriguing aspects of the Ophiuchus discovery. It's forcing astronomers to reconsider what they thought they knew about the maximum power output of supermassive black holes. For decades, theoretical models suggested that there were fundamental limits to how much energy a black hole could extract from infalling matter and convert into jet power. These limits are set by basic physics, the efficiency of converting mass into energy through accretion processes, the maximum rate at which material can fall into a black hole without creating so much radiation pressure that it blows itself apart, and the theoretical maximum energy that can be extracted from a rotating black hole through what's known as the Penrose process. The Ophiuchus explosion appears to push right up against these theoretical limits, suggesting that whatever happened there represents black hole activity operating at maximum theoretical efficiency for an extended period. It's like discovering that someone has built a car engine that operates at 100% thermodynamic efficiency for years on end, something that should be impossible according to our understanding of how engines work. This has led some astronomers to propose even more exotic explanations. Perhaps what we're seeing isn't the result of normal black hole jet activity at all, but something even more extreme. The merger of two supermassive black holes, each weighing billions of times more than our Sun. When such massive objects spiral into each other and merge, they should release gravitational waves of enormous amplitude and potentially create jets even more powerful than anything a single black hole could produce. The problem with this idea is that supermassive black hole mergers should be extraordinarily rare events, and the timing would have to be just right for us to observe the aftermath. But as astronomers have begun searching for similar cavities in other galaxy clusters, they've found that explosive events on this scale might not be as rare as we initially thought. Several other clusters show evidence of large cavities that could indicate similar explosion events, suggesting that what happened in Ophiuchus might represent a previously unknown but relatively common phase in the evolution of galaxy clusters. This is where the story becomes even more fascinating from a cosmic perspective. If explosions on this scale are happening regularly throughout the universe, they represent a previously unrecognized mechanism for distributing energy and matter on the largest scales. These explosions don't just carve out cavities in their immediate vicinity, They send shock waves propagating across millions of light years, heating up vast quantities of gas, triggering star formation in some regions while suppressing it in others, and fundamentally altering the evolution of entire galaxy clusters. In essence, these supermassive black hole explosions might be one of the primary ways that the universe regulates its own growth and structure formation. Just as a thermostat regulates the temperature in your house by turning heating and cooling systems on and off, these massive explosions might serve as a kind of cosmic thermostat, preventing galaxy clusters from becoming too dense, too massive, or too active in their star formation. But let's pause for a moment and consider the sheer temporal scale we're dealing with here. The Ophiuchus explosion began roughly 390 million years ago, during the Devonian period on Earth. This was a time when our planet looked nothing like it does today. The supercontinent Pangaea was still forming, the first trees were just beginning to evolve, fish were starting to develop primitive lungs and venture onto land, and somewhere in the constellation Ophiuchus, a supermassive black hole was beginning an explosion that would continue for longer than complex life has existed on our planet. The explosion continued through the rise of amphibians, through the evolution of reptiles, through the appearance and extinction of the dinosaurs, through the rise of mammals, through the entire evolutionary history that led to the emergence of human beings. It was still going on when our earliest human ancestors first looked up at the night sky and wondered about the lights they saw there. It might have continued until just a few million years ago, essentially yesterday in cosmic terms. And here's perhaps the most mind-bending aspect of this temporal scale. The light from this explosion, the actual photons created by the superheated gas being blown outward by the jets, is still reaching Earth today. When astronomers observe the Ophiuchus cluster with X-ray telescopes, they're seeing light that was created hundreds of millions of years ago by one of the most powerful explosions in cosmic history. In a very real sense, we're witnessing ancient history, preserved in the form of electromagnetic radiation that has been traveling across the universe for longer than complex life has existed on our planet. This preservation of ancient events in the form of light is one of the most poetic aspects of astronomy. Unlike archaeology, where we dig through layers of earth to uncover fragments of the past, astronomy allows us to observe the past directly, to see the universe as it actually was millions or billions of years ago. Every photon that reaches our telescopes is a time traveler, carrying information about events that happened when the universe was younger, when galaxies were forming, when the first stars were being born. But the Ophiuchus explosion tells us something even more profound about the nature of time and change in the universe. We tend to think of cosmic events as either instantaneous, like supernovas that flare up and fade away in a matter of months, or eternal, like the steady burning of stars that continues for billions of years. The Ophiuchus explosion represents something in between, a sustained, violent process that continued for longer than most species exist on Earth, but which is still just a brief moment in the life of a galaxy cluster. This intermediate timescale is crucial for understanding how the universe evolves and changes. Stars form and die on timescales of millions to billions of years. Galaxies merge and evolve over billions of years. But the processes that shape the largest structures in the universe, the galaxy clusters and superclusters that form the cosmic web, operate on these intermediate timescales of tens to hundreds of millions of years. The Ophiuchus explosion gives us a rare glimpse into one of these intermediate scale processes actually happening, allowing us to study cosmic evolution in action rather than just inferring it from static snapshots. From this perspective, the cavity in Ophiuchus becomes something like a cosmic fossil, preserving evidence of a dynamic process that would otherwise be impossible to observe directly. Just as paleontologists can reconstruct the behavior of extinct animals from fossilized bones, astronomers can reconstruct the physics of supermassive black hole explosions from the cavities they leave behind in the hot gas of galaxy clusters. And this fossil record is telling us some surprising things about the history of our cosmic neighborhood. The Ophiuchus cluster is one of the nearest major galaxy clusters to our own local group, the small collection of galaxies that includes the Milky Way. In cosmic terms, we're practically next-door neighbors. This means that the explosion we're studying didn't happen in some exotic, distant corner of the universe where conditions might be very different from our own region. It happened right here, in the same cosmic neighborhood where our own galaxy has been quietly evolving for the past 13 billion years. This proximity raises fascinating questions about what effects, if any, such a massive explosion might have had on our own cosmic environment. Could the shock waves from the Ophiuchus explosion have reached our local group? Could they have influenced the formation and evolution of our own galaxies in ways we haven't yet recognized? These are questions that astronomers are only beginning to explore, but they highlight the interconnected nature of cosmic evolution. Even events that happen hundreds of millions of light years away can potentially influence the cosmic environment in which our own solar system formed and evolved. The discovery in Ophiuchus also highlights the incredible detective work that modern astronomy requires. The cavity that reveals this ancient explosion is invisible to ordinary light telescopes. It can only be detected by observing X-rays emitted by the hot gas that fills the space between galaxies in the cluster. These X-rays are absorbed by Earth's atmosphere, so they can only be studied using space-based telescopes like NASA's Chandra X-ray Observatory and the European Space Agency's XMM Newton. Even then, detecting the cavity required sophisticated image processing and analysis techniques. The X-ray emission from galaxy clusters is incredibly complex, with hot gas at different temperatures and densities, creating a complicated tapestry of bright and dim regions. Picking out the signature of an ancient explosion from this complex background is like trying to spot the shadow of a cloud that passed overhead yesterday by looking at today's landscape. It requires not just sensitive instruments, but also theoretical models that can predict what such an explosion should look like and how its signature might be preserved in the hot gas of the cluster. The fact that we can detect such ancient explosions at all is a testament to the incredible sensitivity and sophistication of modern astronomical instruments. The Chandra X-ray Observatory, which provided the crucial data for the Ophiuchus discovery, was launched in 1999 and is still operating more than 2 decades later, despite being designed for a 5-year mission. Its mirrors are so precisely shaped and polished that if they were scaled up to the size of Earth, the largest imperfection would be less than 6 feet high. This incredible precision allows Chandra to create images of the X-ray universe with a resolution that would have been unimaginable just a few decades ago. But instruments alone aren't enough. The Ophiuchus discovery also required the development of new theoretical models and computational simulations that could predict how such explosions should evolve over time. Astronomers had to solve complex equations describing how jets from supermassive black holes interact with the surrounding hot gas, how shock waves propagate through galaxy clusters, and how the cavities created by these explosions should appear in X-ray observations. These simulations revealed something surprising. Explosions powerful enough to create the Ophiuchus cavity should be accompanied by shock waves that heat the surrounding gas to even higher temperatures than normal. When astronomers looked for this signature in the Chandra data, they found it exactly where the models predicted it should be. The gas surrounding the cavity is indeed hotter than the gas elsewhere in the cluster, providing independent confirmation that what they were seeing was indeed the aftermath of an enormous explosion. This combination of observational detection and theoretical prediction represents modern astronomy at its best. It's not enough to simply observe something unusual and speculate about what it might be. Modern astronomical discoveries require a combination of cutting-edge observations, sophisticated theoretical models, and careful statistical analysis to distinguish real phenomena from instrumental artifacts or chance alignments. The Ophiuchus discovery also illustrates how astronomical knowledge builds upon itself over time. The theoretical framework needed to understand this explosion didn't develop overnight. It built upon decades of research into black hole physics, jet formation, galaxy cluster evolution, and X-ray astronomy. Scientists like Roger Penrose and Stephen Hawking developed the theoretical understanding of how black holes can extract energy from infalling matter. Radio astronomers mapped jets from active galactic nuclei across the cosmos. X-ray astronomers discovered that galaxy clusters are filled with hot gas that can preserve the signatures of ancient explosions. Each of these individual discoveries might have seemed abstract or purely academic when they were first made. Who could have predicted that Penrose's theoretical work on black hole energy extraction in the 1970s would be crucial for understanding an explosion detected in X-ray data from the 2010s? This is the beauty and power of fundamental scientific research. You never know how today's abstract theoretical breakthrough might become tomorrow's key to unlocking a major cosmic mystery. The Ophiuchus discovery also raises profound questions about what else might be hiding in astronomical data that we haven't recognized yet. If an explosion this enormous could remain undetected for years in well-studied data from a well-known galaxy cluster, what other discoveries are waiting to be made? How many other signatures of cosmic violence are preserved in the archives of space telescopes, waiting for the right combination of theoretical insight and analytical techniques to reveal them? This is one of the most exciting aspects of modern astronomy. Unlike many other sciences, where new discoveries require building new instruments or conducting new experiments, astronomical discoveries can be made by reanalyzing old data with new theoretical insights or improved analysis techniques. The Ophiuchus cavity was hiding in plain sight in Chandra data for years before anyone recognized what it was. This suggests that our current astronomical datasets might contain the signatures of phenomena we haven't even imagined yet. From a philosophical perspective, the Ophiuchus explosion forces us to confront the incredible violence and power that characterizes the universe on its largest scales. We tend to think of space as empty and peaceful, perhaps because that's how it appears from our comfortable position on the surface of a small, stable planet orbiting a quiet, middle-aged star. But the universe revealed by modern astronomy is anything but peaceful. It's a place where entire galaxies collide and merge, where black holes millions of times more massive than our sun periodically explode with the power of trillions of supernovas, where shock waves propagate across millions of light years, reshaping the cosmic landscape. And yet, somehow, in the midst of all this cosmic violence, conditions have remained stable enough in our local cosmic environment for life to emerge and evolve on at least one small planet. The Ophiuchus explosion happened just 390 million years ago, practically yesterday in cosmic terms, and yet life on Earth continued to evolve and diversify throughout the entire duration of that explosion. The shock waves and high-energy radiation from one of the most powerful explosions since the Big Bang apparently had little or no effect on the development of life in our solar system. This raises fascinating questions about the resilience of life and the factors that make cosmic environments suitable for biological evolution. Are we living in an unusually quiet and stable region of the universe? Or is life more robust than we imagine, capable of surviving and thriving even in cosmic neighborhoods where explosions of unimaginable power periodically reshape the local environment? These questions become even more intriguing when we consider the possibility that other civilizations might exist elsewhere in the universe. If intelligent life has arisen in other galaxies, in other galaxy clusters, what would their experience of cosmic violence be like? Civilizations that developed in the immediate vicinity of the Ophiuchus explosion would have experienced a very different cosmic environment from our own. Their night sky would have been lit by the glow of superheated gas. Their radio telescopes would have detected the roar of jets propagating at nearly the speed of light. Their understanding of the universe would be shaped by direct experience of cosmic violence on a scale we can barely imagine. This perspective highlights one of the most profound insights that comes from studying cosmic explosions like the one in Ophiuchus. The universe is far more dynamic and violent than our local experience would suggest, but it's also far more vast and diverse. What seems like unimaginable violence on the scale of galaxy clusters becomes just another background process when viewed from the perspective of the observable universe as a whole. The Ophiuchus explosion, for all its incredible power, affected only a tiny fraction of the cosmic volume, leaving the vast majority of space completely unaffected. This scale perspective is crucial for understanding our place in the universe. We exist in a cosmos where explosions more powerful than anything we can imagine happen regularly, where entire galaxies are torn apart and rebuilt, where the fundamental structure of space and time is constantly being reshaped by forces beyond our comprehension. And yet, we also exist in a cosmos vast enough that most of it remains peaceful and stable, where small planets around ordinary stars can provide stable environments for billions of years, where life can emerge and evolve and eventually develop the intelligence to study the very forces that shape the cosmic environment. The Ophiuchus explosion thus tells a story that is simultaneously humbling and inspiring. Humbling because it reminds us of the incredible violence and power that characterizes the universe on its largest scales, forces so vast that they make our entire solar system seem like a grain of sand in a hurricane. But also inspiring because it demonstrates the incredible power of human intelligence and creativity to detect and understand phenomena that occurred hundreds of millions of years ago and hundreds of millions of light years away. Think about what an extraordinary achievement this discovery represents. A small group of scientists, working with instruments built by thousands of engineers and technicians, funded by the collective resources of human civilization, managed to detect the signature of an explosion that began when life on Earth consisted of primitive fish and early amphibians. They used theoretical models developed over decades of research to interpret patterns in X-ray data that revealed the physics of supermassive black holes operating at the limits of what should be possible. This is human intelligence and scientific collaboration at its most impressive. We are a species that evolved from simple organic chemistry on the surface of a small planet, and yet we have developed the tools and techniques to study the most powerful explosions in the universe, to understand the physics of objects millions of times more massive than our Sun, to trace the history of cosmic events that happened long before our species existed. The Ophiuchus discovery also highlights the incredible interconnectedness of scientific knowledge. Understanding this explosion required insights from general relativity, developed by Einstein more than a century ago. It required knowledge of black hole physics, developed by theoretical physicists in the mid-20th century. It required understanding of plasma physics, the behavior of hot gases under extreme conditions, the formation and evolution of galaxies and galaxy clusters, and the techniques of X-ray astronomy. No single person could have made this discovery alone. It required the accumulated knowledge and tools developed by thousands of scientists working in dozens of different fields over more than a century. This is how modern science works at its best, as a collective human endeavor where individual discoveries build upon the work of countless others, where theoretical insights developed in one context find unexpected applications in completely different areas, where the tools and techniques developed for one purpose reveal phenomena that no one had imagined. Looking toward the future, the Ophiuchus discovery opens up entirely new avenues for research and exploration. Astronomers are now systematically searching other galaxy clusters for similar cavities, trying to understand how common these massive explosions really are and what role they play in cosmic evolution. They're developing more sophisticated theoretical models that can predict how such explosions should evolve over time and what signatures they should leave in different types of observations. New space telescopes currently under development will be able to study these phenomena in unprecedented detail. The European Space Agency's Athena X-ray Observatory, scheduled for launch in the 2030s, will be sensitive enough to detect much smaller and more distant cavities, potentially revealing a whole population of cosmic explosions that we haven't discovered yet. Ground-based telescopes are being equipped with more sensitive radio and optical instruments that can study the shock waves and heated gas associated with these explosions. But perhaps most exciting of all are the theoretical implications of the Ophiuchus discovery. If explosions this powerful are happening regularly throughout the universe, they represent a previously unknown mechanism for transporting energy and matter across cosmic distances. They might be one of the primary ways that the universe regulates its own evolution, preventing galaxy clusters from becoming too massive or too active in their star formation. Understanding these regulatory mechanisms could be crucial for understanding why the universe looks the way it does today, why galaxies have the sizes and properties we observe, why stars form at the rates they do, and ultimately, why conditions in the universe have remained stable enough for the emergence of life and intelligence. This brings us back to one of the most profound questions in all of science. Why does the universe seem so perfectly tuned for the existence of complexity, life, and intelligence? The physical constants that govern the behavior of matter and energy, the initial conditions that determined how the universe evolved after the Big Bang, the mechanisms that regulate star formation and galaxy evolution, all seem to be precisely calibrated to allow for the emergence of the complexity we see around us. The Ophiuchus explosion might be part of the answer to this question. These massive feedback mechanisms, where supermassive black holes regulate their own growth and the evolution of their host galaxy clusters, might be one of the ways the universe maintains the delicate balance between order and chaos that seems necessary for the emergence of complexity. Too little feedback, and galaxy clusters would become too dense and massive, with star formation rates so high that most stars would be massive and short-lived, leaving little time for the slow processes of chemical evolution that create the heavy elements necessary for planets and life. Too much feedback, and galaxy clusters would be blown apart entirely, with star formation suppressed to the point where few stars would form at all. The explosions, like the one in Ophiuchus, might represent the universe's way of maintaining a middle path between these extremes, providing just enough feedback to regulate galaxy and cluster evolution without completely suppressing the processes that create the complexity we observe around us. From this perspective, the violence revealed by the Ophiuchus discovery isn't just destruction for its own sake, but a necessary part of a cosmic regulatory system that makes complexity and life possible. The same forces that can carve cavities in galaxy clusters and reshape the cosmic landscape on scales of millions of light years might also be the forces that have maintained the conditions necessary for life to emerge and evolve in quiet corners of the universe, like our own solar system. This is perhaps the most profound lesson from the Ophiuchus explosion. The universe is simultaneously more violent and more carefully balanced than we ever imagined. Forces of unimaginable power regularly reshape the cosmic landscape, but they do so in ways that somehow maintain the overall stability and complexity that make our existence possible. We live in a universe where explosions more powerful than anything we can comprehend happen regularly, where the space between galaxies is filled with the echoes of ancient violence, where supermassive black holes periodically unleash forces that can reshape entire galaxy clusters. And yet, we also live in a universe where small planets can orbit ordinary stars in peaceful stability for billions of years, where the slow processes of stellar nucleosynthesis can create the heavy elements necessary for rocky planets and organic chemistry, where life can emerge and evolve and eventually develop the intelligence to study the very forces that have shaped its cosmic environment. The Ophiuchus explosion thus becomes not just a story about cosmic violence, but a story about cosmic balance, about the incredible fine-tuning that allows complexity and life to exist in a universe governed by forces of almost unimaginable power. It's a reminder that we exist not despite the violence of the cosmos, but because that violence is part of a larger system of checks and balances that has somehow managed to create and maintain the conditions necessary for our existence. And perhaps most remarkably of all, it's a story about the power of human curiosity and intelligence to detect and understand phenomena that challenge the very limits of what should be possible. The Ophiuchus explosion happened hundreds of millions of years ago, in a region of space so distant that its light takes longer to reach us than complex life has existed on Earth. And yet, through a combination of careful observation, theoretical insight, and scientific collaboration, we have managed not just to detect this ancient explosion, but to understand its physics, to trace its history, and to recognize its role in the larger story of cosmic evolution. In the end, the Ophiuchus explosion tells us something profound about both the universe and ourselves. The universe is vast and violent and governed by forces beyond our everyday experience, but it is also comprehensible, governed by physical laws that human intelligence can discover and understand. We are small and fragile creatures living on a tiny planet in a vast cosmos, but we are also part of the universe's way of understanding itself, conscious beings capable of studying and appreciating the incredible complexity and beauty of the cosmic environment that created us. The cavity in Ophiuchus will persist for millions of years to come, a permanent scar in space that preserves the memory of one of the most powerful explosions since the Big Bang. Future generations of astronomers will study it with instruments we can't yet imagine, discovering new details about its physics and its role in cosmic evolution. But they will also be studying something more: evidence of humanity's growing ability to detect and understand phenomena at the very limits of what should be possible. Proof that intelligence and curiosity can reach across vast distances and enormous spans of time to comprehend the forces that shape our universe. The largest explosion since the Big Bang happened in a place so distant that its light has been traveling toward us since before complex life existed on Earth. But in detecting and understanding that explosion, we have somehow made it part of our own story, part of humanity's growing understanding of our place in a cosmos that is simultaneously more violent and more wonderful than we ever dared to imagine.